to WQNJ having me here on February 8th. I'm really thrilled to be here. It's kind of an emotional journey because the last time I was on campus was at the opening of the Cheng Library. And both my parents are gone now, so I'm looking forward to spending a little time over there, which I've never had the opportunity to do. It's very meaningful for me to be a guest here. I appreciate it. The last time I gave this talk, it was to a conference of computer geeks who, and I say that with the utmost respect, and they accept that terminology, actually. They were largely mathematicians and computer programmers. And today I'm speaking, I think, mostly to musicians, so I'm amongst my own more. I will be wearing both my performer and my college professor hats because I sometimes inhabit a classroom at UCLA where I teach seminars in contemporary music and performance. I'm not a mathematician, but I actually have trouble remembering numbers, but my focus today is going to be on the math that underlies and has been manipulated by the evolution of musical style over the centuries. And as another effort to understand, although never really fully understand ever, the mystery of how an acoustic phenomenon, which we call music, can sometimes move us to tears. I myself had a traditional music training that took me through the great works of Bach, Beethoven, Chopin, Debussy, and even an early introduction by my piano teacher of Bloomfield, New Jersey, Isabel San Ambrosio, who serendipitously presented me with the sans serif white album of Henry Cowell's piano music when I was about 12. And I think planted the seed of my ending up devoting my life to my performing career, to commissioning and performing music by living composers. Music in the 20th century, especially after World War II, became often unmoored from traditional principles of tonal harmony. Music, as always, expresses the individuality and unique voice of the composer, but now we have a plethora of styles emanating from the ever-richer musical worlds that composers now have access to. Composers nowadays, unlike Mendelssohn and Chopin, which we all listen to, practice, composers nowadays can listen to music from every era and every genre. The era of a common practice has long been gone, and we're now in the era of unique practice. Composers, you are unique and you are complex, and you often write music that stretches and sometimes even reverses some of the techniques that I learned as a piano student. It's an undeniable challenge to learn works in musical languages that are as numerous and distinctive as the people who composed them. But over time and with a lot of practice for us performers, a musical profile emerges, a syntax comes into focus, a sensibility reveals itself, and we in our practice rooms finally, gradually start to realize the communicative power of a new and original musical means of expression. My performance interests extend, in addition to contemporary, extend also to Renaissance and Baroque harpsichord music. This copy of a 1769 French model by Pascal Tasquin was built for me by my amazing husband in our garage, 500 hours in the garage, and we hired a sign maker to copy some of the original decorations on the soundboard, and those on the left are how it all started, the blueprint and just the unfinished frame. I did nothing to help except choose the colors. Exploring the repertoire written for this instrument is what put me face to face with the long and contentious history of tunings and temperaments and the amazing math that guided their evolution. I'm sure that some of you already know that the mathematics of tuning a keyboard instrument provoked intellectual and philosophical clashes of the highest order and involved some of the great minds, including Euclid, Newton, and Copernicus. the centuries-long acceptance for the tuning of a piano, these big black monsters that we now play, which we also take as a given, was shaped by and also a driver of composers' imaginations. In other words, the evolution of musical style through the centuries. I am barely a subconscious mathematician, but in any case, the intersection of math, acoustics, and the development of the keyboard and the great music written for it is the fascinating story. So we're going to dive into a little bit of history first. The idea of that music and math are related dates from ancient times. The 6th century BC philosopher Pythagoras posited that numbers in natural ratios, whole number ratios, and proportions were principles that governed everything in the universe, from astronomy to musical harmonics to the sense of justice to the purity of the soul. It was a universe based on mathematical principles of harmony. The notion of music's ability to give sensual pleasure was deemed not only to be the least of its attributes, but a perversion of its true purpose and a crime against the natural order. So we have the Pythagoreans who linked the study of arithmetic, astronomy, geometry, and music as the quadrivium, or the four roads in Latin, but Latin came later. It was named that later, which together with the trivium of grammar, rhetoric, and logic comprised the 7 liberal arts of classical antiquity and the basis of many university programs today. Music, or at least most of it, is based on proportional relationships, whole number integers. Pythagoras, with his famous monochord, proved some of the original principles that we use, that we refer to today.
You hear the same pitch as the open string, but an octave higher. Now I will divide the string 3 and place it on the 3rd. I hear a 5th above the original note.
A perfect fifth, in other words.
When divided into 4, I hear the same original pitch, but one more octave higher. And 5 will give me a 3rd above the original note.
A perfect third.
Can you guess what I got?
A triad. In other words, the basis for a triad. So these are known as the Pythagorean ratios, based on the acoustical overtone series. And these are the perfect intervals and the integers that comprise them. 2 to 1 is the octave, 3 to 2 the perfect fifth, 5 to 4 the major third, the perfect major third, and etc. These perfect ratios are what make a piece like this, played entirely on the piano strings, possible. This is the one piece where my father patted down in his slippers and listened to me practicing and said I was playing it too fast. He said, no, you have to, it's gongs, you have to play it slow, and so the temple bells, the giant bells, they has to carry all the way over the valleys to the other village, and you have to slow it down. So I took his advice, it was very good advice. So Pythagorean tuning was the predominant system of tuning for over 1,000 years. And this is the harmonic series as it is acoustically, I'd like to play this for you. A sine wave is the only really pure sound that lacks overtones. So we're hearing the pure pitches of the harmonic series now. The left is an approximation on the piano keyboard of the harmonic series. And the lower is the difference between the pure harmonic series and what we use as equal temperament. We're at the B flat now. You can hear how flat it is. Number 10. So that's cool, isn't it? Those are the pure whole integer proportions, pitches that we get from those proportions. So if you're going to tune your keyboard instrument according to Pythagorean principles, you tune them in perfect fifths, and then you switch them around in order to stick them in within an octave, and you've got a major scale. The problem is there were some issues with this. It may have been perfect for Greek music. So you can hear that the ancient Greek music was largely monophonic, melodic, and not having to do with harmony. When we get into harmony and we start using Pythagorean tuning in perfect fifths and then transposing everything into one octave to get our scales, we have issues. And this is called the historical tuning problem. We find that if tuning in perfect fifths, you end up not at the same place that you started. B sharp is not the same as C. It's not a circle of fifths, it is a spiral. The problem is that fifths, perfect fifths, are just a little bit too large to fit into the sacrosanct octave. And it throws the octave into, as well as many other intervals, very out of tune. The octave is inviolable in Western music. It's not so in every single musical culture. But what happens is that in Western music, our inviolable octave becomes violated by an amount which is called the Pythagorean comma. Okay? So how far off are we exactly? For you mathematicians, this is how much the difference is between, say, a C and a B sharp. So this is the problem. We're off by this number of hertz, or about 23 cents, knowing that 100 cents is a semitone, two adjacent keys on the keyboard, or nearly 1/4 of a half step. We're mixing some fractions here, but half step being a C to a C sharp, 1/4 of that pitch distance is how much we're off, and it is enough to hurt our ears. So how do we get the math to work out? We make the math work out so for everything to fit in an octave and still sound in tune. We distribute that Pythagorean comma all around the circle of fifths. We make them all a little bit smaller, perhaps. There are various, as you can see, various efforts to solve the problem. We distribute, we detune, we temper. We temper the Pythagorean comma, and that's how we call them. That's why we call them temperaments. The dissonances get spread around either equally in equal temperament, and that's very small, I'm sorry, but in equal temperament, you just divide the Pythagorean comma by 12 and reduce the distance between the pitches by that much, so everything is equal. In the well temperaments, on the right, they will find different ways of doing it you can see different fractions between the pitches, and often they will put in a very obscure part of the circle of fifths, like between G sharp and E flat. They will, or G sharp and D sharp, if you want to call it that. They will put a different interval in there because nobody's going to really hear that unless you're writing a piece in the key of G sharp, which is not going to happen very often. If you do, you rotate your circle and you can place your that interval elsewhere. That interval is called the Wolf interval, and we're going to talk about that in a moment. The thing is, these ones on the right kind of mean tone. They sort of take the mean of they massage that Pythagorean comma, and again, in various ways. You have these mean tone temperaments, Silberman, Werkmeister. These are all various efforts to make a solution. But what happens is these mean tone temperaments favor thirds. And what it worked for very well is Renaissance keyboard music, which they loved thirds, as you can hear. Look at all those thirds. Those of you who have really amazing ears might notice that the fifths are a little bit small, but the thirds are beautifully, beautifully in tune. And that suited the Renaissance composers. I hate to, I'll give you a little more of that, okay? Just because it's so beautiful. What do you think? Gorgeous. Yeah. So this suited 16th century music, and it persisted for well over a century, these kinds of temperaments. They followed the demands of composers' imaginations, and in turn dictated the evolution of keyboard instruments, and in turn determined musical style. It's this amazing a symbiotic relationship going here that keyboard instruments and their makers had to accommodate. So I've gotten into the math about as deeply as I'm going to. No more math. But I was very curious, since I now have a harpsichord, I was really curious to hear myself what the difference between equal and Pythagorean might be. Like, could I really hear it? So let's hope this works. But a better example might be actually hearing a piece of music. So this is a work by Bach. It's unlikely that Bach would have used Pythagorean. He probably would have used one of the later versions, well temperament, certainly not equal temperament. It hadn't been invented yet. But composers were imagining more harmonic freedom to write in all 24 keys by this time. And I'll just play for you just the opening of this beautiful C-sharp minor prelude from Book 1. And let's see, I can try to, which one would you like to hear first? Equal. Let's see if I can get that to work. Okay. What do you want to hear next? Well? Oops, sorry. I can't. It's hard to control. And here's well, hopefully. You want to hear one other in comparison? Just the opening. Want to hear equal just to compare with what you just heard? What do you think? It's very subtle, I know, but I'd say Pythagorean really was the loser. Especially that. Okay. There is a theory now, I don't know if maybe some of you have heard about this, that recent research from 2005, not that recent, I guess, Dr. Bradley Lehman suggests that Bach actually specified the tuning that he used. We don't really know. We're just imagining that he may have used one of those mean tone temperaments, and there are so many of them. But Bradley Lehman posits that this squiggle that Bach put on his title page of the Well-Tempered Clavier is actually code for his temperament system. And he has an article about that you can look up yourselves, but he calls it our Rosetta Stone, that he kind of just, offered it, but put it in a very encoded manner, and that someday somebody might figure it out. So it is probably a well-temperament because it's called the well-tempered clavier, not the equal-tempered clavier or the Pythagorean-tempered clavier. So we just don't know which one of those well-temperaments he used. I want to talk about that Wolf interval for a second. They usually will place if you're going to tune, let's say, Pythagorean, and you've got these perfect fifths, acoustically perfect fifths, and then you end up with this fifth, which is 24 cents. Flat. That's the Pythagorean comma, 23 point, whichever this is rounded up to 24. I wanted to hear it for myself, how bad is it? So I'm going to first play it for you here. That's fine. White keys, C to G. It's okay. But once you get off the white keys, all right. I'm glad you hear your reaction. I wanted to do that myself, so on my harpsichord, we have this. It's not as pretty. But listen to this one. Bad, right? That one's bad. I'm glad you agree. So, fixed pitch instruments like the keyboard oblige players and their extremely long-suffering instrument makers to accommodate composers' desire for more harmonic freedom and to write in more than just the white keys. So they created these split keyboards sometimes, when this shows the mathematical offsets of in cents, if you can see those. In cents, so that you can write a piece, say, in G sharp major, or in F sharp major, and just choose which one of the split keys you use. So I'm going to just show you one of these instruments. And a piece that really exploits the possibilities of these instruments. In a diatonic mode, chromatic. It's wild, isn't it? But this instrument would enable Nicola Vincentino to play in that many keys. It's not a great piece of music necessarily, and it would not work. If we were to play that in equal temperament, it would lose all of its character. But it enabled Vincentino to actually write in that many keys and have it somewhat within each key area to be somewhat in tune with itself. Some contemporary composers really revel in this howling wolf interval and other dissonant intervals as a way to expand the tonal color palette of a piece of music and immerse us in a different sonic reality, like from Lamont Young, for instance. And once you live in this sonic reality for a while, equal temperament will sound very odd to you. I'll just fast forward a little bit. This is from a piece called The Well-Tuned Piano from 1964, and it's a 6-hour piano solo work. This is just an excerpt from it. It's a largely improvised work. Preparing the piano itself to live and stay stable in this tuning takes weeks. The piano is very, very much resists this kind of tuning, but he and also Terry Riley actually had their home pianos tuned in a temperament other than equal temperament because they disliked equal temperament. And here's what Terry did. He's using a combination of very consonant and very dissonant intervals. So to make a piano sound like that, it's a totally different world. You like it? Yeah. It's cool. So equal temperament is not the be-all and end-all. It's in fact, equal temperament is a decidedly microtonal scale, but we don't talk about it because we're so brainwashed that it's the be-all and end-all, but it's not. The tradition of creating instruments like Vincentino did, or like Terry Riley and Lamont Young, what they do to their instruments to transform them. It lives on. Harry Partch was probably one of the earliest to create all kinds of things to suit his compositional imagination. He used found parts. These are gongs, cones from an airplane, from Douglas Aircraft. He got these cloud chamber bowls from Berkeley, the radiation labs in Berkeley, and hubcaps and that kind of thing. I'll show you one of his instruments that is not equal temperament. This is called the diamond marimba. And just learning to play this instrument takes some doing. All of those instruments are the Partch instruments. They actually lived at Montclair State University for a while. And now a whole collection of them is living in LA. They went to Seattle for a while, I think. Anybody know anything about that? There's a large collection of them now in LA and played by a group that call themselves Partch. So although equal temperament is the most common tuning system in the West by distributing those small intonational defects or Pythagorean commas equally amongst the 12 tones of the chromatic scale, as I say, it's microtonal. It is microtonal if we compare it with the acoustical phenomenon of tuning. And it achieves consistency by sacrificing perfect interval ratios. So those whole integer ratios are no longer. The uniformity between adjacent pitches or key areas allows any musical pattern to be replicated anywhere and still sound the same. Higher or lower, but still sound the same and be in tune. It also, as you might imagine, neutralizes the distinct character of each key signature, scale, or mode. And acceptance did not come easily for equal temperament. It is still contentious today. They have airport novels now, airport books, for the general public. Stuart Isakoff's book called Temperament, and a newer book called How Equal Temperament Destroyed Classical Music. So there are still people who really decry the move to equal temperament, but without equal temperament, so much of the music that we know and love would never exist, like jazz, like the music of Messiaen, like the chromaticism of the late Romantic period. It could not have come about without equal temperament. As composers forged ahead creating musical styles that followed the evolution of tuning and temperaments, and vice versa, as composers inspired the evolution of tuning and temperaments. The increasing chromaticism of the late Romantic period opened the door to atonality, as you probably know, Wagner, and then Schoenberg, who created his method of composing with 12 tones, in other words, the 12-tone method. And it was actually a solo piano work, the Suite Opus 25, in which Schoenberg first applied it. After the Second World War, and again, I think in an effort to maybe bring some order to a chaotic world, a period of strict systematization followed this seminal experimental piano etude by Olivier Messiaen, who was the inspiring mentor to Pierre Boulez's Karl-Heinz Stockhausen, Iannis Xenakis. And this is his system where mode de valeur et d'intensité, in other words, a mode of values, note values. So here we have his row of 12 durations ordered in a row. And intensité, in other words, the attacks, the articulations, the attacks, and the actual dynamics, in addition, of course, to the pitches. So these are his pitch rows, decorated with the applied rows that apply to the dynamics and the articulations. And he has 3 modes that interact with each other. Amazingly enough, and this is a picture of me, very young. Amazingly enough, it sounds like music in the hands of a Messiaen. And that's where this is. The Greek composer Iannis Xenakis is the composer most noted for integrating his training as a mathematician, architect, and civil engineer in his music. He was deeply inspired by the natural environs of Greece, and who isn't? But also as a mathematician, he realized that natural phenomena are calculable. And we know that chaos, what's so-called chaos, the butterfly effect, that these things can be mathematically equated and calculated. Probabilities, whether it be, in Xenakis' case, one of the inspirations was the student protests in Athens around the end of World War II, where he could hear the students demonstrating and chanting a slogan in one part of the plaza, and then another one starting up here, out of sync, of course, and then another one here, that one starts to fade, and another one starts here. And those polyrhythms were one of the things that actually, the probabilities of those events happening could be calculated. So could the next round of gunfire. He was injured in one of those demonstrations. And that moment was actually another very deeply inspirational, fundamental inspiration for his music. He wanted to portray the moment, the sounds that he heard at the moment the shrapnel hit his face. If you can imagine that, and you listen to his music, and it suddenly makes sense. And the violence of it, the absolute noise of it, it's of course microtonal. And it's just, that to me is so profoundly moving that a composer, an artist, would use that traumatic event in his life as an inspiration for his art. So he brought mathematical processes to his note choices, rhythm, and structures, including set theory, probability theory, new forms of calculus, and game theory. He also made seminal contributions to the development of electronic and computer music, and his aim was to give musical compositions the same absolute correctness as a mathematical equation. He was exiled for 30 years in Paris because the Greek government, the right-wing government, had a death sentence over his head. So he exiled himself to Paris, worked with Le Corbusier as an architect, famously designed the Phillips Pavilion in Brussels. You probably studied that in music history. And most of his teachers, including Honegger, Millot, Nadia Boulanger, they failed to understand him, but Boulanger had the good sense to send him to Olivier Messiaen, who did understand him. By using parabola-type shape, that these are string, this is a sketch for an orchestral score called Metastasis. For 61 players, 1-2 apart, you bypass the having to conform to a scale. You just do a glissando, and you take in every pitch possible. This starts very quietly. And if you look at this sketch for Pithepracta, which means has a meaning of probabilities, it means probabilities, another orchestral piece. It actually, you can see that natural phenomena were an inspiration for him. It almost looks like a flock of birds or insects. And again, he calculated, to see these sketches up close is amazing, because each one of these points, pre-calculated, pre-computer, was mapped out. By the use of his mathematical expertise. This is supposed to be largely about the keyboard, though, so I do want to... he is dealing with... He's emulating mist, the thermodynamics of a vapor. Again, he could calculate that using stochastic distributions and mathematical functions that show the probability of random variables. Maybe a mathematician out here knows what I just said. But he's portraying the movement, the thermodynamics of gaseous substance. And I think this is amazing. Doesn't it sound a little bit like a mist? A little bit? Like a cloud? On the other hand, Xenakis never claimed that a rigorous or an analytical basis is sufficient to produce a well-formed piece of music. For anyone who's partially informed about the mathematical theory and expect the music to be a mirror of mathematical processes and equations, his music is no more a translation of probability theory than an artichoke is a translation of the Fibonacci series. He's still a musician. And when you listen to his music, knowing something about his background, it can be extremely powerful. The violence makes sense, the parabolas make sense. He was just an amazing artist. Music has grown in complexity, but some of my favorite keyboard music has no rhythm. I'm going back to the keyboard now because rhythm, although it's not a specifically keyboard element, I'm going to, explain it in the context of keyboard music. These are the unmeasured preludes of Louis Couperin, who was the uncle to the more famous Louis le Grand Couperin. And these were, if you look at the notation of this, no time signature. It's just the freedom given to the performer is fairly infinite. You play the pitches, but at the timing and the pacing that you want. And if you've ever heard a guitarist like noodling around trying to tune the instrument, this is sort of what he had in mind. He was inspired by lutenists who were kind of warming up and making sure that all the strings of their lute were in tune with each other. So the rhythm is whatever you want it to be. This is not the score to this. So it allows the performer to be completely free, and every performance will probably be different. This was one of my earliest performances on the harpsichord, and when I came face to face with someone who said, "Oh, you're going to play Louis Couperin. What temperament are you going to use?" And prior to that, I had never thought about it. And suddenly, I'm immersed in the world of temperaments, and it's been fascinating to learn about. So as music has become more complex, as our rhythms of life have become more complex, we see Hindu meters that Olivier Messiaen applied, his use of the non-retrogradable rhythms and his rhythmic rows, Greek meters in the music of Elliott Carter, cross rhythms and multi-layered polyrhythms from sub-Saharan Africa, inspiring Steve Reich and Giorgio Ligeti, and interlocking rhythms of the Indonesian gamelan, which we hear in the music in jazz, as well as in the music of Thomas Addis. Kamen Nankara was by far one of the most innovative musical minds of the 20th century, and in his pursuit of rhythmic virtuosity, he wrote almost exclusively for the mechanical player piano. He produced some of the most rhythmically complex music ever written, and shamelessly flaunted intricate contrapuntal systems using up to 12 simultaneous tempi. Despite its complexity, Nankara's music is infused with his love of the jazz pianism of Art Tatum and Earl Hines. So here's one example. And the ingenuity that it took to compose these works for the player piano and sit there and notate it and then punch holes. The imagination is amazing. I'm going to show you now when humans try to play it. Thomas Addis did a transcription of this, but it cannot be done at his tempos, at Nankara's tempos. The notation is really complex. The uplets that you have to try to coordinate with each other it took a lot of rehearsal to get that. It was in another piano work, Fabric, by early 20th century composer Henry Cowell, who really kind of was groundbreaking in advocating for a new notation system that would accommodate something other than just duple, dividable by two divisions of the beat. So he, for quintuplets, just do this, and septuplets, and they're uplets, but he wanted to also have a notation to indicate that. So this is his work, Fabric. That's very beautiful. We'll listen to the whole thing. So Henry Cowell was, he was the teacher of not only George Gershwin, but also John Cage. And he just, in writing in 1930, he criticized the existing system as incapable of representing any except the most primary divisions of the whole note. And he was right. We still don't really have a notation to indicate different kinds of uplets. But Thomas Addis came up with the idea of irrational time signatures. And I'm going to show this one to you because my friend Stephen Taylor, who teaches at University of Illinois, wrote this piece for me. And you'll notice time signatures like 5/12, 6/14, 7/20. And what do those mean? Well, what happens is, let's talk about 5/12. 12/12 is a 4/4 bar, right? Yeah? Okay? 6/12 would be a 2/4 bar. But what he wants is only 5 of those sextuplets, not all 6. So you do the timing of a sextuplet, but you don't play all 6. You only play 5 of them. Likewise, a 7/14 bar would be a 2/4 bar, correct? Yeah, would be a 1/2 or a 2/4, and a 7/14. So instead of 7 septuplets, you just play them 6 of them in the time of a septuplet. You want to hear what it sounds like? Yeah. So what he's really trying to do is just get the spurting of a fountain, and if you're not looking at the score, it's a lot easier. It just sounds like the irregular, it sounds like a fountain of water, does it not? I think he actually captured the sound of water droplets in this piece and how they, and then they fall. What do you think? Anyway, so in conclusion, musicians, like mathematicians, are inspired by the quest for beauty, whether it be in the form of a sonata or an elegant proof. They both embody complex ideas, abstract meanings, unique relationships, and persuasive narratives that make sense through logic or through sound. Music and math both value patterns and harmony in form and structure. Through a series of perfect imperfections, Western music comprises a universe of sensual, emotional, and intellectual expression that we now enjoy. And as I play the music written for the harpsichord and the very different music for the piano, and maybe if you find yourself at a Baroque music concert, followed by a jazz recital next door, we might remind ourselves of really the centuries-long tale of how we got here. So thank you very much.